Okay, thank you for your kind introduction. And I'm a PhD student of Southeast University of China. And today I'm happy to share with you about my research progresses on experimental study of dual mode control MEMS thermal wind sensor with high accuracy. Well, my presentation will be structured by the following 5 parts. First, I will introduce the background of MEMS thermal wind sensor. And then I will talk about the design and principle. And after that, I will show the fabrication and packaging process. Also, I will give the experimental results and discussions. Finally, I will make a brief conclusion. And now let's move on the first part, background of MEMS thermal wind sensor. We know that we are entering into an era of the so-called Internet of Things, where sensors are playing an important role. So, of a variety of sensors, wind sensor has important applications on many areas. For example, weather forecast, aviation, navigation, high-speed ground transportation, wind-generated electricity, and also agricultural production. So, what's the advantages of MEMS thermal wind sensor? When compared with the traditional mechanical wind sensor, the advantages can be is no moving elements, fast response, and also high sensitivity. And when compared with the ultrasonic anemometer, the advantages can be its ability of quantity production, low cost, and also minimization. So, based on the MEMS thermal wind sensor, one important theory is the calorimetric principle. When an airflow blows over the chip sensor, the calorimetric flow sensors usually consist of a heating source and spatially separated temperature detectors. When an airflow blows over the sensor, heat transfer includes the thermal convection to the air and also the thermal conduction through the substrate. So, let's look at this picture. When there is no flow, the sensor is heated by the heating resistor and the temperature field on the sensor is symmetrical. So, but when an airflow blows over the sensor, the temperature field of the sensor will change. A forced heat convection occurs from upstream to downstream, and then a temperature gradient will generate. So this generated temperature gradient is then a measure of wind. Based on calorimetric principle, there are several kinds of operation modes categorized by the control mode of the heating resistor. 2 main operation modes can be the constant power mode and the temperature balance mode. First, for the constant power mode, it means the heater is heated by a constant power, and we detect the temperature difference of the upstream and downstream thermistors as the output signal. Well, in practice, it's sometimes replaced by the constant voltage operation. For the temperature balance mode, by adjusting the heating power of the upstream heater and downstream heater, we cancel the flow-induced temperature gradient along the chip. So this power difference of the upstream and downstream heaters are the measure of wind. In this paper, we propose a dual-mode control thermal wind sensor combining the constant voltage mode and the temperature balance mode to achieve a high accuracy measurement of the full measurement range. So now I will show the design and principle. Well, this is a picture of the schematic layout of the sensor working in the 2 different operation modes. The left side shows the layout of the constant voltage mode, where the heaters are located at the inner side and thermistors are located outside, while in the temperature balance mode, the situation is on the contrary. Well, also the control circuits of each mode are shown at the lower place. As for the output signal, in the constant voltage mode, we give the heaters a constant voltage and we detect the temperature difference between upstream and downstream thermistors as the output. Well, in the temperature balance mode, we keep the temperature difference between upstream and downstream thermistors zero through this feedback control system, and we detect the heating voltage of upstream and downstream heaters as the output signal. Well, now I will show the fabrication and packaging process. This sensor was fabricated on ceramic substrate directly using a two-step MEMS leaf-off process. First, the photoresist was patterned on the ceramic substrate, and then platinum resistors was sputtered and patterned as the heating resistors and also the thermistors. Well, finally, a gold layer was sputtered on the sensor to form ties for wire bonding using the same leaf-off process. So this is the photograph of the fabricated wind sensor. Also, the temperature properties of the fabricated platinum resistors was measured to be about 2,450 ppm per K. Well, so how do we package the sensor? Because the sensor was fabricated on ceramic substrate, a self-packaged method was adopted by using the back surface of the ceramic substrate as the airflow sensing surface, and the resistors was sealed with bonding glue after wire bonding. After that, the chip sensor was glued to the metal frame and finally installed in the protection shell. So why do we choose ceramic as the material of the substrate? It has some advantages. For example, it can provide a smooth surface for airflow sensing, and also an appropriate thermoconductivity. Also, it has stable mechanical property together with this easy packaging method. Well, after fabrication and packaging, we did experiments. This wind sensor was put into a wind tunnel for wind speed and wind direction test. The wind speed of the wind tunnel can be up to 33 meters per second. And we can see from this picture, the output voltage of the sensor of both modes increased with the increasing wind speed. And also the calculation of wind speed and wind direction was listed here for the two operation modes. There are a little bit difference. Also, wind direction measurements was made. This picture shows the output voltage versus the wind direction at several different wind speed. We can see for north-south direction and east-west direction, they each has a sine and a cosine relationship with the changing wind degree. In order to evaluate the measurement accuracy of the sensor, the sensor was first calibrated and put into the wind tunnel for test again. From the measurement results, we can see that at a low wind speed, that means under 10 meters per second, the constant voltage mode has less error. And for high wind speed, that means up to 33 meters per second from 10 meters per second, the temperature balance mode is better. Well, so when we combine the two operation modes together, the sensor can achieve a high accuracy with the speed error of less than 0.3 and the direction error of less than 2 degrees. Well, now I will make a conclusion of my work. This paper proposed a dual mode control MEMS wind sensor combined by constant voltage mode and temperature balance mode. The sensor consisting of 8 resistors was fabricated on ceramic substrate using MEMS leaf-off process. Also, experimental results show that the wind sensor detects wind speed up to 33 meters per second with an error of less than 0.3, and the measured direction from 0 to 360 degrees has an error of less than 2. While For our further research, we may focus on the theoretical foundation of the dual mode control wind sensor, and also we may investigate the temperature effect of the sensor to see whether it will change with the ambient circumstance. And that's all about my presentation. Thank you for your attention.